Okay, in this video, we're going to go through and practice proving trigonometric identities. And an identity is where you have an equation where the left side is always equal to the right side. And the reason why we practice these is so that we can get comfortable manipulating and using algebraic techniques to simplify or change expressions that have trig functions in them. And that way, once we get comfortable with that, the next step is to use those techniques to solve equations with trig functions in the equation. Now, some of the identities that we'll be using to substitute will be these right here. These are the most common, so I wanted to put it right in the notes at the top so we can refer to it if we need to, which I can guarantee you we will go back and use some of these. And some of the algebraic techniques, or the most common techniques that we're going to be using, are these 7 right here. Now, that's not to say that there aren't other methods that we'll use, but these are the ones that we'll use frequently. Now, when you are proving a trigonometric identity, the easiest way to go about this is to look at the equation and pick the side that is the most complicated. Pick the side that has lots of fractions or square roots. Pick the side that is the most complicated because that means there's more there that you can work with. And you want to just work on that one side and try to use these techniques to manipulate that side to show that it's equal to the other side. So when you're working with these trig identities, you really want to stay working with just one side. If you start switching sides, it's going to get confusing and it's going to lead to a mistake. So really just try to stay on one side. I can't stress that enough. Okay, so what I've done is I've listed a couple of examples for each of these techniques to illustrate how you can use these to prove a trig identity. So the first technique we're going to use, and this is my go-to technique. This is the technique I use if I'm really, really stuck and I can't figure out anything else. This is what it comes down to. And this is probably the most popular technique as well. Is you change all your trig functions and all your expressions in terms of sine and cosine, and then you try to simplify it. So if you notice, this side I would consider the more complicated side. There's not a whole lot you can do with sine squared. We have a secant here, and I'm going to rewrite that so that it's in terms of cosine. So I'm going to write cosine theta, and then in parentheses, I'm going to rewrite secant as 1 over cosine theta. So that is our reciprocal identity, minus cosine theta. And that's equal to sine squared theta. So notice I'm not touching the side. I'm just carrying it down. What I'm doing is manipulating the left side and trying to show that it's equal to the right side. So now my instinct tells me to just distribute. So I have cosine over 1 times 1 over cosine. That will give me a 1. Then I have cosine times a negative cosine. That will give me a negative cosine squared theta. So again, notice I didn't touch this side. I'm just carrying it down. Okay, now this is where you might want to refer to one of your identities above. The 1 minus cosine squared theta actually comes from one of our Pythagorean identities. So we have the identity cosine squared theta plus sine squared theta is equal to 1. That was one of our Pythagorean identities above in the shaded blue box. If I solve this for sine squared theta, that means I subtract cosine squared theta from both sides. And I can take 1 minus cosine squared theta, and I can substitute in the sine squared theta. So notice, I'm going to put that in for this. And now I have just showed 6 sine squared theta is equal to sine squared theta, and I just proved my identity. Okay, the next example, again, there may be more than one technique to these, but right now I'm showing you how to use or writing your expressions in terms of sine and cosine. So I am going to rewrite tangent in terms of sine and cosine. Tangent is sine x over cosine x, and that's all over sine x. So I just rewrote tangent as sine over cosine. And I'm just bringing down my secant. I'm not touching it. I'll finish this up over here. Okay, now when you have a fraction divided by a fraction, you flip and multiply. So I have sine x over cosine x, and I'm going to multiply that by 1 over sine x, because if you notice, I can write this sine x as sine over 1, so when I flip it and multiply, that's going to be 1 over sine. And again, I'm just going to carry down the secant x. I'm not touching the right-hand side. So all I did up to this point is rewrote my expression on the left-hand side in terms of sine and cosine, and now I'm setting it up to try to simplify it. So I can cross off my sine, and I'm left with 1 over cosine x is equal to secant x. And as you know, secant and cosine are reciprocal, so 1 over cosine x is secant x. So I just showed that this identity is true. So those two examples were showing how you can write everything in terms of sine and cosine, and then use your algebra skills to try to simplify it and show that the left and the right-hand side of the equal sign are the same. Okay, the next technique is by splitting up a fraction. So typically we have two fractions. We want to find a common denominator and add them together and combine them into one fraction. But one of our techniques is to take one fraction and break it into two fractions. So I'm going to take 1 plus sine theta over cosine theta and break it into two fractions and try to simplify it. So I'm going to rewrite this as 1 over cosine theta plus sine theta over cosine theta. I'm not touching the right-hand side. I'm just bringing it down. Okay, so now I have 1 over cosine theta plus sine theta over cosine theta because they split it up into two fractions. And as you know, 1 over cosine theta is equal to secant theta because secant and cosine are reciprocals. And sine theta over cosine theta is tangent theta. So we just showed that the left-hand side of that equation is equal to the right-hand side, and we just proved that identity, so we're good to go. Okay, sticking with the same idea of showing how to split one fraction into two fractions and try to simplify, I'm going to rewrite secant squared x minus 1 over secant squared x into two fractions. So I have secant squared x over secant squared x. I'm going to subtract 1 over secant squared x. And I'm going to show that that's equal to sine squared x. Okay, so I split it up into two fractions. Now secant squared x over secant squared x, I can rewrite that as 1. Secant and cosine are reciprocals. I can rewrite 1 over secant squared as cosine squared. Now, if we think back, we have that Pythagorean identity that cosine squared x plus sine squared x is equal to 1. And if we rearrange that, we get that 1 minus cosine squared x is equal to sine squared x if I just subtract cosine squared x from both sides. So 1 minus cosine squared x is equal to sine squared x, so I can replace 1 minus cosine squared x with sine squared x. I think my pencil's running out of battery power. I have to go charge it soon. So I have sine squared x is equal to sine squared x. And we just proved that identity as well. The next technique we can use to prove identities is using factoring. So in part A, this left-hand side here, I can factor out a cosine x. And what would be left over would be 1 minus sine squared x. And I'm going to just bring down the cosine cubed x. Now, using Pythagorean identity, I know that 1 minus sine squared x is equal to cosine squared x. And cosine times cosine squared is going to be cosine cubed. So we just proved example A for factoring. So in the second example for factoring, we have cosine squared plus 4 cosine plus 4. So this is like a trinomial that we need to factor. So when we factor this, we're going to have cosine t plus 2 times cosine t plus 2 in order to get cosine squared plus 4 cosine in the middle and then plus 4 on the end. The 2 and the 2 would give me the 4 here. And if I take cosine times 2 and cosine times 2 and add them up to get the middle term, that will give me 4 cosine. And then the cosine times the cosine in the front will give me cosine squared. So you should always multiply it back out to check it if you're not familiar with factoring expressions that have trig functions in them. Okay, so now we have all of this over cosine t plus 2, and this is equal to 1 plus 2 secant t all over secant t. Now, I can cross off what they have in common, the cosine t plus 2, cosine t plus 2, and what I'm left with is cosine t plus 2 is equal to 1 plus 2 secant t all over secant t. Now, I'm trying to get the left-hand side to be the same as the right-hand side. So if you notice, I have a denominator here of secant t. So I want to try to make a denominator of secant t on the left side. So I'm going to write this over 1, and I'm going to multiply the top and the bottom by secant t. So when I take secant times cosine, so I got to take this times this, and then this times this, the secant times cosine, and then the secant times the 2. Secant times cosine is going to give me 1. And that is because secant and cosine are reciprocals. Cosine can be written as 1 over secant, or secant can be written as 1 over cosine. When I multiply them together, I get 1. If I take secant times 2, I get 2 secant. And then on the bottom, I have secant times 1, which is just secant. And that is all over. And that is equal to 1 plus 2 secant over secant. And we just proved our identity. Okay, in the next two examples, I'm going to show you the technique of combining fractions and how that can help you prove an identity. So here we have two fractions. I want to find a common denominator so that I can add them together. So I'm going to multiply the first fraction by cosine x on the top and the bottom. So I'm taking the first fraction, cosine x over 1 plus sine x, and I'm multiplying the top and the bottom by cosine x. And then on the second fraction, I want to multiply the top and the bottom by 1 plus sine x, so I get a common denominator. And I want to show that that's all equal to 2 secant x. So when I multiply, and I'm looking at the first fraction, I get cosine squared x all over cosine x times 1 plus sine x. When I multiply the second fraction, I have to distribute here. I have 1 plus sine x times 1 plus sine x. So when I FOIL that, I'm going to get 1 plus 2 sine x plus sine squared x. And that's going to be all over common denominator of cosine x times 1 plus sine x. And I want to show that that's 2 secant x, so I'm just going to keep carrying this down. Now, because I have a common denominator here, I can combine the tops. If you notice here, I have cosine squared x plus sine squared x. And I know that my Pythagorean identity says cosine squared x plus sine squared x is equal to 1. So I can take out that cosine squared x and the sine squared x and replace it with a 1. So I have now on the top, I have 1 plus 2 sine x all over cosine x times 1 plus sine x. And I'm just going to carry down again on the right hand side 2 secant x. The 1 and the 1, I can make that a 2. And if I factor out a 2 in the numerator, I have 1 plus sine x left over on the inside of the parentheses, and then in the denominator I have cosine x times 1 plus sine x. And that's all equal to 2 secant x. Now I can get rid of the 1 plus sine x on the top and the bottom, which leaves me, I'll finish it over here because I'm starting to run out of room. That leaves me with 2 over cosine x is equal to 2 secant x. As you recall, secant and cosine are reciprocals, so I can pull that cosine up in the numerator as a secant. Because if I flip it upside down, it becomes secant. So that becomes 2 secant x is equal to 2 secant x. And we just showed that that big mass with those two fractions on the left is all equal to just 2 secant x. Okay, the next example, again, we're trying to show how we can use finding common denominators and combining fractions. We can use that method to prove identities. So I'm going to make a common denominator here and combine the fractions. So for the first fraction, I'm going to multiply the top and the bottom by 1 plus cosine x. Then for the second fraction, I'm going to multiply the top and the bottom by 1 minus cosine x, and this will give me my common denominator. And I want to show that that's equal to cosecant squared x plus cotangent squared x. So when I multiply this first expression That's going to give me 1 plus cosine x on the top with 1 plus cosine x and 1 minus cosine x in the denominator. When I multiply the second expression, I get cosine x minus cosine squared x, because don't forget I have two terms here multiplying it by this. I got to use distributive property. And then on the bottom I have 1 minus cosine x, 1 plus cosine x. So I have my common denominator now, so I can combine my fractions. And I want to show that that's all equal to cosecant squared x plus cotangent squared x. So if you notice here, I have a subtraction. So that means I have to subtract all the terms in that second fraction. So that's going to be a minus cosine and a minus minus cosine squared. That makes this a plus. So I have 1, then cosine x minus cosine x. These are going to disappear. And then I'm left with plus cosine squared x. And this is all over 1 plus cosine x times 1 minus cosine x. And I want to show that that's equal to cosecant squared x plus cotangent squared x. Now down here, I have the difference of squares. If I actually go ahead and multiply that out, what I would end up getting in the denominator is 1 minus cosine squared x. And if you recall, that is equivalent to sine squared x. So now I have 1 plus cosine squared x over sine squared x. Because we FOILed the bottom and got 1 minus cosine squared x because it's the difference of squares. And 1 minus cosine squared x is equal to sine squared x using Pythagorean theorem. Now, if I simplify that fraction and I write that as 1 over sine squared x plus cosine squared x over sine squared x, and I split that fraction up to simplify it, that's going to give me cosecant x squared, because sine and cosecant are reciprocal. So if I take that sine squared and bump it in the numerator and I flip it upside down, it's going to become cosecant squared. And cosine squared over sine squared is equivalent to cotangent squared. So I just showed that this is equal to this. And we are done. Okay, the next technique I want to show you is multiplying by the conjugate. And a quick refresher, conjugates are numbers that are written so that when you have two terms, the middle sign changes. So for example, a plus b and a minus b are conjugates. Notice that the signs of both numbers don't change. It's just the sign in the middle between the two numbers is what changes. And that's what makes it a conjugate. If both signs change of both those numbers, then it would be the complete opposite. That would be the opposite. So let me make a note of that. If you have a plus b and then you have minus a minus b, those are opposites. Versus conjugates, which is just the sign in the middle that changes. So, for example, in A, I'm going to take the left-hand side And I'm going to multiply the top and the bottom by the conjugate of 1 plus cosine x. And the conjugate of 1 plus cosine x is if I just switch that middle sign. So the conjugate would be 1 minus cosine x. I'm going to multiply both the top and the bottom of that fraction by the conjugate of 1 plus cosine x. As long as you do it to the top and the bottom, you can do that. And I want to show that this is equal to 1 minus cosine x all over sine x. So I'm just going to copy that down. So when I do that, on the top, I get 1 minus cosine x times sine x. On the bottom, because I have 1 plus cosine x and 1 minus cosine x, that's the difference of squares. So when I multiply that out, I get 1 minus cosine squared x because the middle term just disappears because of the plus and the minus. And a lot of times the benefit to doing that is because you're putting it in a possible form that we can use Pythagorean, one of the Pythagorean identities. So the 1 minus cosine squared, I can rewrite that as sine squared. That's the Pythagorean identity. So I have 1 minus cosine x times sine x all over 1 minus cosine squared is sine squared. And I want to show that that's equal to 1 minus cosine x over sine x. Now, notice the denominator in the right-hand side, what we're trying to get or rewrite this expression as, I want a sign in the bottom. And right now on the left-hand side, I have 2 signs in the denominator because I have a sine times a sine. So I'm going to simplify this and get rid of a sign on the bottom and a sign on the top. I'll finish up over here. That's going to leave me with 1 minus cosine x. When I get rid of a sign on the top and the bottom, I'm still left with 1 sign in the denominator. And that's what we were trying to do all along, so we just finished proving that identity. Okay, the second example of using conjugates, I'm going to do the same thing. On the left-hand side, I'm going to multiply the top and the bottom by the conjugate of 1 minus sine. Now, the conjugate of 1 minus sine would be 1 plus sine. Remember, you change the middle sign so that you get the difference of squares. So I'm going to multiply by 1 plus sine theta over 1 plus sine theta. And I'm going to multiply that by cosine theta over 1 minus sine theta. And I'm trying to get that to be the same as secant theta plus tangent theta. Well, on the top, I have cosine theta times 1 plus sine theta. And then in the denominator, when I take 1 plus sine times 1 minus sine, that's the difference of squares. So I'm going to get 1 minus sine squared theta. Sorry, my pencil battery is running low. And I'm trying to get that to equal secant theta plus tangent theta. Well, 1 minus sine squared theta is equal to cosine squared theta. So I have cosine theta times 1 plus sine theta. And that's all over cosine squared theta. Now, I can get rid of one of the cosines. And so I'm left with 1 plus sine theta over cosine theta. And then I can split that fraction up into 1 over cosine theta plus sine theta over cosine theta. 1 over cosine theta is secant because they're reciprocals. And sine theta over cosine theta is tangent. So we just proved that the left-hand side was equal to the right-hand side. And we are done. Okay, now we're going to use other identities to substitute to prove the trig identity that's given to us. So in this first example, if you notice, we have negative angles. And whenever we're dealing with negative angles, it's really a good idea to think back of our even and odd functions so that we can get rid of those negative angles. So when we have an even function, like cosine, I'll put example, cosine of a negative angle, because it's even, is going to be the same as cosine of just that angle without the negative sign. And when you have odd functions, for example, if you have sine of a negative angle, then that's the same as negative sine of that angle. So we're going to use properties of even and odd functions to make these substitutions so that we can simplify the left-hand side. So what I'm going to do is, everywhere I see sine of negative theta, I'm going to replace it with negative sine theta. And everywhere I see cosine negative theta, I'm going to replace it with cosine theta because of our even and odd properties. So I'm going to rewrite sine squared negative theta as sine of negative theta, and I'm going to square it. So that way we don't mess up our negatives because of the squares. I'm going to rewrite this first. And cosine negative theta squared. And I'm just going to copy everything else down. And we're trying to show that all of that is equal to cosine minus sine. Now I'm going to replace sine of negative theta with negative sine theta. When I square it, it'll become positive. So if you notice, let me take this out now. Sine negative theta, I can replace that with negative sine theta because of my properties of odd functions. And then when I replace cosine of negative theta with cosine theta, this is what we have. So the part that's in red, I use my properties of even and odd functions to replace and make that substitution. So now let's continue from here. When I have negative sine theta times negative sine theta, that negative is going to turn into a positive. So I have sine squared theta. And that's going to give me minus cosine squared theta all over. Now I'm going to use that same substitution again. Sine of negative theta is going to become negative sine theta using my properties of odd functions. And then cosine of negative theta is going to be replaced with cosine theta using my properties of even functions. And I want to show that that's equal to cosine theta minus sine theta. Now, in the numerator, I have the difference of squares, so I can rewrite the numerator as sine theta plus cosine theta times sine theta minus cosine theta and factor it. And in the bottom, I can pull out a negative 1, and I'm left with sine theta plus cosine theta. And I want to show that that's equal to cosine theta minus sine theta. Now I can get rid of the sine plus cosine theta on the top and the bottom, and I'm left with negative sine theta minus cosine theta. And I want to show that that's equal to cosine theta minus sine theta. Well, if I distribute that negative sign, that's going to give me a negative sine and a positive cosine. Which is exactly what we were trying to prove. So we are done with that one. This next example actually is 2 steps, because right away I noticed that this is equivalent to cosecant theta. If I look back in my blue shaded box, that's one of my Pythagorean identities. 1 plus cotangent squared theta is equal to cosecant squared theta. And remember, when you multiply reciprocals, you get 1. Sine squared theta times 1 over sine squared theta. Because cosecant and sine are reciprocals, cosecant squared theta is equivalent to 1 over sine squared theta. And when I multiply reciprocals, I get 1 over 1, which is 1. So that one was a nice easy one. And all we used was the substitution for my Pythagorean identity. Okay, last example, we're going to use even and odd function properties again, because I see a negative angle in there. So the first thing I'm going to do is I'm going to rewrite this without the negative angles. So I have tangent x, and I'm going to rewrite this as plus sine x, because sine of negative x is the same as negative sine x. This negative with the negative that's already in the expression make it a positive. I have a double negative. And that's going to all be over 1 plus cosine x. And I want to show that that's equal to tangent x. Well, the next thing I probably want to try is either writing everything in terms of sine and cosine, or maybe try multiplying by the conjugate. Now, both will probably work. Let's start with one, and if one doesn't work, we'll try the other. I'm going to start by writing everything in terms of sine and cosine and trying to simplify. So I'm going to rewrite that tangent as sine x over cosine x. I want to show that this is tangent x. So I'm just going to copy that tangent x down. Now, I want to get rid of the complex fractions. So I'm going to multiply everything by cosine x. So I'm going to multiply the top by cosine x and the bottom by cosine x. Let's see if this does anything. If not, we'll just try something else. Sometimes that happens. So when I multiply cosine x times sine x over cosine x, the cosines disappear and I'm left with sine x. When I take cosine x times sine x, that gives me cosine x times sine x. And on the bottom, of course, I have cosine x times 1 plus cosine x. And we want to show that that's equal to tangent x. Let's see. On the top, I can pull out a sine x, and I'm left with 1 plus cosine x, and that's all over cosine x times 1 plus cosine x. And I want to show that that's equal to tangent x. If you notice, I can get rid of the 1 plus cosine x. Those factors are the same, so those divide out to be 1. And I'm left with sine x over cosine x. And as you know, sine x over cosine x is tangent x, so we just showed that the left-hand side is equal to the right-hand side, and we are done with that one. The last method I want to show you is just multiplying and simplifying. So in example A, we've got two parentheses, or two quantities that we need to multiply together. Now this, before we multiply, I notice right off the bat that I can simplify that and make that sine squared x. That way I only have to distribute once instead of twice. Now if I didn't simplify that, it's totally fine. It just would have been a little bit more work. Where this way, I'm just distributing the sine squared x. Either way would have worked. So now I'm going to distribute the sine squared x and multiply through. So I have sine squared times 1, so I get sine squared. And then sine squared times cotangent squared. And I want to show that all that is equal to 1. Well, this I can simplify. Cotangent, if I rewrite this in terms of sine and cosine, cotangent squared is cosine squared over sine squared. So if you notice, when I multiply, I can get rid of the sine squared. So now I'm left with sine squared x plus cosine squared x, which is equal to 1. And we know this is one of our Pythagorean identities. Sine squared x plus cosine squared x is equal to 1. We just proved this identity and we're done. I have sine x plus cosine x and x squared. So I've got to write sine x plus cosine x times sine x plus cosine x. And I want to show that that's equal to 1 plus 2 sine x cosine x. Well, I have to multiply this out and distribute twice. I have sine x times sine x. That gives me sine squared x. Then I have sine x times cosine x. Then I have sine x times cosine x again, which makes this a 2, because I have 2 of them. And then I have cosine x times cosine x, which gives me a cosine squared x. And I want to show that that's equal to 1 plus 2 sine x cosine x. Using our Pythagorean identity, I know that sine squared x and cosine squared x, when I add them together, gives me 1. So I can take this out and replace it with 1. So I have 1 plus 2 sine x cosine x, and that's equal to 2 sine x cosine x, and we just finished proving that identity, and we are done. So in general, just to sum up, all these techniques I've showed you are just tools in a toolbox that you have. It doesn't mean you have to always use these specific ones. You might come across a different method that you find that works easier. And sometimes when you're proving an identity, you have to use multiple tools and multiple methods. So there isn't always one way to do something. Sometimes there's more than one way. And I might do it one way and you might do it another way, but we're still going to be able to prove that that identity is true. So all the examples I did in here, I bet if I went through them again, I could find alternate ways to do them. So I don't want you to think there's only one way to do it. So just make sure you understand the tools that you have available to you, and those rely highly and heavily on your algebra techniques. But just make sure that you go back and review those algebra skills if you're not strong, because you are going to need those.